Look at a molecular cloud through a telescope, and it appears to be a serene, solid mass hanging motionless in space. But the mathematical reality is quite different. We are looking at a highly compressible, swirling, chaotic fluid system. Astrophysicists divide star formation into two distinct physics problems. The microphysics governs how a single, dense core collapses entirely into a newly formed protostar, eventually spinning into an accretion disk. The macrophysics dictates everything leading up to that point: how giant molecular clouds form, how they evolve, and what ultimately drives them to fragment. We are isolating the macrophysics. For decades, the standard model treated giant molecular clouds as quasi-static spheres, held in a slow, stable equilibrium, supported against gravity by internal magnetic fields. Current research focuses on a different model, one where the macrophysics of star formation are governed by large-scale, supersonic, and highly compressible turbulence. This introduces a strict mechanical paradox. On a macroscopic scale, this turbulence provides the kinetic energy necessary to counteract gravity. It supports the total mass of the cloud, preventing it from collapsing inward all at once. But because the internal velocities are highly supersonic, the gas cannot absorb the kinetic energy smoothly. The turbulence drives extreme, localized compressions throughout the entire cloud structure. The same mechanism supporting the cloud is actively crushing gas on a small scale, triggering the formation of stars. To understand how stars form, we have to look past the assumption of equilibrium and map the nonlinear mathematics of supersonic fluid dynamics. The baseline physical state of a giant molecular cloud is defined by extreme velocities. The internal velocity dispersion, the random movement of the gas, vastly exceeds the local sound speed. The entire environment is highly supersonic. This chart plots velocity structure against spatial scale. Classical Kolmogorov turbulence cascades energy conservatively, yielding a shallow slope of 1/3, but supersonic interstellar gas dissipates energy directly through violent shocks. This Berger's turbulence creates a steeper slope of 1/2. Numerical simulations reveal a major consequence of this shock network. The turbulent energy does not linger, it decays rapidly, typically dissipating within a single flow crossing time of the cloud. We calculate this turbulent dissipation time as approximately 1/2 the cloud diameter divided by the line of sight velocity dispersion. For a typical cloud, that kinetic energy drains away in just a few million years. Because the kinetic energy bleeds out so quickly, giant molecular clouds cannot be closed systems. They require a continuous injection of fresh kinetic energy from massive external forces, like galactic shear or supernovae, to prevent immediate catastrophic global collapse. Shifting the analytical focus from the velocity of the flow to the density of the gas clarifies the physical impact of these supersonic shockwaves. The intersecting flows continuously compress and rarefy the gas in every direction. In fluid dynamics, each passing shockwave acts as an independent, multiplicative random variable, altering the local density of the cloud. Applying the central limit theorem to these multiplicative shockwaves forces the gas density into a log-normal probability density function. As velocities become more supersonic, the variance widens, pushing gas into an extreme high-density tail. In three-dimensional space, these density variations have specific geometric consequences. The initial lower amplitude compressions force the gas to settle into curved stagnation sheets. Where those stagnation sheets intersect, the gas is compressed even further. This forms the dense, fractal filaments universally observed by radio telescopes inside molecular clouds. The clumpy interior of a molecular cloud is the mathematical output of a log-normal probability distribution, driven by the Mach number of the flow. To evaluate the role of magnetic fields, we use the Lagrangian virial theorem to weigh the competing forces of kinetic, magnetic, and gravitational energy. This balance is expressed as the virial parameter. When a cloud is globally bound by gravity, but supported against immediate collapse, it sits near an equilibrium state, where the virial parameter is approximately equal to 1. To determine if magnetic fields provide that support, we calculate the magnetic critical mass. This is the theoretical threshold where the mass of the gas creates enough gravitational energy to overcome the tension of the local magnetic field lines. Modern Zeeman effect measurements show that the mass-to-flux ratio surpasses the critical threshold of 1, typically reaching a value of 2. These clouds are magnetically supercritical. Gravity is stronger than the mean magnetic field from the moment the cloud forms. Historically, theorists proposed ambipolar diffusion, where neutral gas slips past rigid magnetic field lines to gather mass. But calculations show this scale is microscopic, about 0.05 parsecs. The magnetic field remains firmly frozen to the gas on macroscopic scales. Since these clouds are born supercritical and magnetic diffusion is too slow to operate on large scales, magnetic fields cannot prevent gravitational collapse. This leaves supersonic turbulence as the primary regulator of star formation. This graph brings the macro and micro models together. For a star to be born, a localized pocket of gas must exceed the thermal pressure limit, represented by this vertical dashed line. This is known as the Bonner-Ebert mass. Large-scale velocity dispersion keeps the total cloud's virial parameter near 1, preventing global collapse. However, variance in our density distribution is driven by that same supersonic turbulence. The flow mathematically pushes gas past that threshold, populating the extreme tail of the PDF. Physically, this represents dense gas cores fragmenting out of the turbulent flow. Past the critical mass limit, they detach and begin gravitational collapse. Stellar birth is a mathematical consequence of compressible turbulence, a statistical outcome of the cloud's internal motion. The fraction of gas pushed into the high-density tail of the PDF dictates the overall star formation rate of the entire galaxy. The galactic scale consequences are visible here. Every bright cluster and active stellar nursery across this galaxy is the direct physical output of turbulent mathematics. Astrophysics has transitioned from modeling static, magnetically supported spheres to viewing molecular clouds as dynamic, self-regulating fractals. The laws governing these clouds are scale invariant. The same fluid dynamics operate everywhere, from local stellar nurseries to massive giant molecular associations in distant galaxies. The next logical step is applying this large-scale turbulent fragmentation to the microphysics to determine how these compressions set the precise mass distribution of the stars themselves, the initial mass function. The chaotic nurseries of the universe are bound by rigorous scaling laws. The turbulence that prevents a cloud from collapsing also engineers its fragmentation, dictating the structure, evolution, and luminosity of the cosmos.